All right, well, good evening, and welcome to Kopernik Observatory. It's great to have practically a full house. My name is Drew Desker. I'm the director here, and again, it's I was, as we were driving up here, I was thinking, man, well, it's good. It's not, unfortunate weather conditions, and unclear how many people will actually come here tonight, and you guys have proven me wrong, so thank you. Just as a matter of interest, who's here for the first time? Okay, practically everybody. Okay. Then next question is, who here is a member of Kopernik? Okay, the rest of you, I guess. So for the people who raise their hand first, notice the people that raise their hand second, they are in a special group of supporters of Kopernik. And being a member actually is a very beneficial thing. Not only can you get up here on any Friday night and for certain special occasions, but also we belong to what's called the Association of Science and Technology Centers, ASTC, and it's a consortium of over 350 other science centers throughout the country and even spread out throughout the world that will honor our Kopernik membership. So if you like this kind of place, and my guess is most of you probably do, you might want to consider getting a membership. We get student memberships, we have family memberships, we have grandparent memberships now. And it's an opportunity to get into some great places. You can go to the Ithaca Science Center, Museum of Science and Technology up in Syracuse. You can go to Roberson. You can go to the Intrepid Museum down in New York City, or the Franklin Institute down in Philly. But again, there's 350 of those up there. Kopernik is an informal STEM education center. We've been around for actually next year will be 50 years that we've been here, and it's an opportunity for us to, we do outreach to schools, we do a very extensive summer camp program, and we do Friday night programs. We really promote lifelong learning. So I'm glad that you're here to feed your mind tonight. Let's see here. We've got a couple of things coming up down the road that might be of interest. Tomorrow night, in fact, actually, is our Race to the Stars 5K race. So if any of you are racers, or even if you walk, you can do this. It's a 5K race that starts here. It's an out and back, and it's on the nice gentle slope portion of not the hill you just climbed up here. So if you're interested, the race will start at 7 o'clock, and you can come up and do that. And then also in June, we have a thing called Rocket Fest, where people and families will come and they'll pick up a rocket kit, like one of those Estes rockets, and they build it at home. And then they come up here. We give them a certain launch window to come in. We'll check out your rocket, and then you get to hit the button that launches your rocket 500 or 1,000 feet up in the sky. And then, if we aim it right, you get your rocket back. That's the goal here. So again, every Friday night we do a public program from March to mid-December, and it's not always about astronomy. Last weekend we actually had a gentleman talking about the Marconi Tower that's in town. I don't know if anybody remember who Marconi is. Marconi was the gentleman who invented radio, basically, and he actually won a Nobel Prize for it. No big surprise there, but what was interesting is that he did a number of experiments, one of which he actually did here in Binghamton. They set up a tower, actually 2 towers in Binghamton, down near the Marabito baseball stadium behind the post office. And there was another set of towers down in Scranton, and they actually used this as an experiment to communicate to a moving locomotive that was going between Binghamton and and Scranton, and so there's actually some real significant radio history that was made here in Binghamton. This week we're doing 20,000 Leagues Over an Alien Sea. Next week will be a program about oceanography. So it's not always about astronomy, but we always promote, again, after our program, if it's clear out, we'll open up our domes and invite you out to look at the night sky through our scopes. And I said, unfortunately, tonight, that's not going to happen. But again, if you paid to get in, we will give you a card to come back on another night. So Anyway, we are going to also. I want to welcome our people watching on the live stream. For those that don't know, we now start. We've been since 2020. We've been live streaming our programs. Actually, back in March of 2020, we had to shut down, and we said, okay, well, we'll just hold off for a couple of weeks until this COVID thing blows over. And well, that didn't exactly play out the way I had planned it. And so by about May, we decided, look, we already have these speakers lined up. Why not have them zoom into here and just turn it back around and put it out on a YouTube channel? We now have 13,000 people subscribed to our YouTube channel. We have done these Friday night programs. We've done special events where, like, we might be watching the launch of when the SpaceX Crew Dragon, the Demo 2 mission, launched back in 2020. It actually had a local astronaut, Doug Hurley. He was the commander of that, and so we did sort of a simulcast, sort of a watch party, taking the NASA feed, but then communicating within the group there, and then did the same thing when when they returned to Earth safely. We've also done a number of live streams of astronomical events. We've done Comet Neowise. Comet ZTF. We've done lunar eclipses, and coming up next year we'll do the solar eclipse. On April 8th, there'll be a solar eclipse that will be here in Binghamton. Will cover about 99% of the sun. So lots of good stuff going on here, and lots of good stuff that's going to go on tonight. We are very fortunate to have once again Zoe Lerner Ponterio from SPIF, the Spacecraft Planetary Imaging Facility. Zoe is a frequent presenter here. We're just about ready to give her own parking spot. And I'm really glad that you're up here tonight because you're really in for a treat. So, Zoe, take it away.
All right. Thank you very much, Drew. And yes, very exciting. Always good to come here to Kopernik. I've been here so many times, and it's always one of my favorite places to visit. I love that there were so many people here who this is their first time to Kopernik. I hope that I make a good impression and that you come back again. For those of you that have seen me talk before, you know that I'm always wearing something space-themed, oftentimes a dress with pockets. But for tonight, given the title, I decided to go sea beasts, though my leggings are still space-themed because we are going to be in space. So we are going to be talking tonight about Jupiter's moon, Europa. And I always try and come up with clever titles, and so I tried to do a 20,000 Leagues Under the Sea theme here. But this, of course, so many of my stories start with, but then I got curious. And I want to know, does anyone know how far a league is? I didn't know either. It turns out it's 3 miles. And so then I thought, well, wait a second, 60,000 miles under the sea? I mean, Earth's oceans at their deepest are 7 miles deep. And I think a lot of people had a misconception that the under the sea meant going straight down, the depth that you were going, but that's actually not what the title refers to. It refers to the distance traveled while under the sea. Even given that, though, the circumference of the Earth is 25,000 miles, so 60,000 miles is still like twice around plus some. Still an awfully long time to be in a submarine. But today we're going to be talking about a very different point of view over an alien sea. And that's because we're going to be looking from space. Now, I tried to come up with some sort of distance that was appropriate for 60,000 miles to 20,000 leagues. Couldn't really come up with much except for the fact that, of course, the big thing we'll talk about toward the second half of the talk will be the upcoming Europa Clipper mission, which will be a spacecraft. And as the spacecraft orbits around during its mission, it will, at certain points, be exactly 20,000 leagues away from Europa. So there we go. There's the connection for you. All right, so before we jump into talking about that, though, I always like to go back and I like to make a story. I like to tell the story of this moon and why we are so fascinated with it. So we're going to go all the way back to when this moon was first discovered. And it was discovered by Galileo, who, as far as we know, is the first person to point a telescope up into the sky and look at Jupiter. And so what you see in the top image there, the bright circle is Jupiter, and then there's the 4 dots. Those are the Galilean satellites, so named because of Galileo. They are the 4 by far largest moons of Jupiter, and they are big. Europa is actually the smallest one, and it's a little smaller than our moon, but Ganymede, the largest one, is also the largest moon in the solar system. It is bigger than the planet Mercury. So these are little worlds unto themselves, honestly. So moons are not all just, oh, old crater to our moon. They are fascinating places. Now, Galileo watched, you can see his notes here, he marked Jupiter with the circle with the star in it, and then the moons as stars, but did he know they were moons? It's unclear. He never refers to them as such, and in fact, at that time, moon was a proper noun. That was the name of Earth's natural satellite. He referred to them in his notes often simply with Roman numerals. In order of their distance from Jupiter, and occasionally referred to them as either stars or planets. So it's not really clear if he understood the connection between these and Earth's moons, but even if he didn't, it didn't take long before people figured that out. Now, people continued to observe these Galilean satellites for centuries, and by the 1960s, we were able to use telescopes to at least tell us what the surfaces were made of. And what we had discovered by that point was that Europa's surface was mostly water ice, which was not too shocking because that turned out to be true for most of the outer solar system moons that we were studying. So Europa was just one of these icy moons. Then we got our first ever up-close image of Europa. And it may not look very impressive, but this was taken by the Pioneer 10 spacecraft in 1973. Pioneer 10 was the first spacecraft to ever venture through the asteroid belt to the outer solar system. Didn't carry the greatest of cameras, but Pioneer was meant to primarily do one thing: demonstrate that we could go to the outer solar system. And it and its partner, Pioneer 11, both demonstrated that beautifully. We honestly were pretty nervous about, can we navigate through the asteroid belt? And I still have people ask me today, oh, well, how do you navigate through the asteroid belt? It's not like in the movies. The asteroid belt is still incredibly empty, and asteroids are on average 600,000 kilometers apart from each other. So my answer to how we navigate it is we shoot straight through. We don't even think about it. In fact, we have to work hard if we want to go visit an asteroid. That's much more difficult to do. But Pioneer 10 and 11 demonstrated that, yes, indeed, it's empty enough that we can go through it and not worry about it. And there was still nothing too remarkable seen about Europa other than, oh, it's got a pretty reflective surface. So then now with the success of Pioneer 10 and 11, it was time to turn towards serious spacecraft, Voyager 1 and 2. And so Voyager 1, just 4 years later, provided us with our first good image of Europa. And so what we saw here immediately was a very bright surface, far more reflective than Earth's moon. The moon is actually pretty dull. It looks bright in the night sky just because, well, you know, what else is there to compare it to? But if you ever get a chance to look at the moon and Earth together, the moon actually looks really dark gray. This is far more reflective. And later on, Voyager 2 passed even closer to Europa, and we really got to see the texture of the surface. And one of the things you'll immediately notice that's vastly different is not seeing a lot of craters, and instead cracks. Cracks everywhere. And so we saw these bands, these ridges, very few craters, and also we did some measurements. This is the smoothest object in the solar system, at least one with a solid surface. Give you an idea. The biggest terrain variations on Europa are only a few hundred meters. So that means that our landscape around us right now, that's the Himalayas on Europa. Now, you could interpret that two ways. On one hand, you could say, oh, well, that seems like it's just this perfect sphere that's just sitting there, not much is happening. But actually, we know that craters are impacting all objects in the solar system and have been all at, the same rate. So when you see such a smooth surface so lacking in craters, it actually tells you the opposite. This surface is young. It is not just sitting there, it is changing. And those old craters are being erased. This is the same reason we don't see a lot of craters here on Earth. Earth is very geologically active, and old craters get erased. So this was really piquing our interest. And when we looked a little bit closer, we started to notice, and I'll go point at them here, places where, here's a great example, this crack stops, gets sliced, and then another crack that looks about the same width continues on. And if you look carefully, you'll start to notice a few other examples of this. And they said, these are cracks on top of cracks on top of cracks. Cracks form, and then the cracks get cracked, and then the cracked cracks get cracked. And this just happens over and over again. So imagine this thing is kind of like a yarn ball. It's cracks all the way down, no matter how far in you zoom in. Now, they said, okay, clearly an active surface. Now, we know that Jupiter has enormous gravity. We know that that creates enormous tidal forces that are going to squeeze and squish all four of these moons, just like we squish the moon and the moon squishes our oceans. And they said, okay, so if this is a rocky core and then an icy coating on the outside, maybe it's just the tidal forces are cracking it. But when they measured the longest cracks, that could not be explained simply by tidal forces cracking a solid ice crust. There had to be something allowing cracks that large to happen. And the answer is lubrication. Something had to allow the surface to slip and slide that much. And so, similar to Earth, where we have our plate tectonics, where our crust is allowed to shift because our plates are floating on top of a lubricating mantle, liquid rock layer, not plate tectonics, but tectonics just the same, the conclusion was that there must be a layer of liquid under here, the most obvious being water. If there's ice on the crust, water underneath. And the models supported this tidal heating model. So what you have here is Jupiter squeezing and tugging and heating up the inside with the friction of that squeezing and tugging and squishing and pulling. And that is creating hot rocky bottom with volcanic activity. That is supported very much by, if you know the moon that's closer, Io is all volcanoes all the time, doesn't have any water ice on it. It's got 400 volcanoes. So we know that Jupiter's gravitational forces can produce volcanoes in a rocky body. Except this rocky body is then covered by a layer of liquid water, which is topped by a layer of water ice. Well, that's really fascinating to find an ocean that, by all estimates, has twice as much water as all of Earth's oceans combined. But okay, so it's an ocean. So what? So this is all happening with Voyager in 1979. The so what is something that happened just 2 years before this. And I want you to appreciate these years I'm throwing out. 79, and next I'm going to talk about something that happened 2 years before in 77. I don't think I'm that old. I was born in 78. So this knowledge is not that old. So the thing that happened in 1977 was the first ever expedition to the deep ocean bottom.
I want the folks online to be able to hear me. All right. Is this now? Okay, that sounds like it's working. Okay, so geologists wanted to go study underwater volcanoes. At that point, 1977, everyone knew that the deep ocean floor was devoid of life. There's no sunlight reaching down there. What would life thrive on? So down they went, not a single biologist on the team. And when they arrived at the bottom, they saw some interesting stuff. They saw fish swimming around, little squid blubbing around, tube worms, some of them 8 feet tall, crabs, krill, little shrimp, clams everywhere. And the person in the submersible radioed up to topside and said, I thought you said there wasn't going to be any life down here. And they said, oh, yep, that's right. And he said, I'm seeing these things. And the people up on the boat actually thought he was hallucinating. So sometimes as scientists, we need to remind ourselves that we don't know everything, and that without data to back up your claim, you better be ready to have it disproven.
Test, test. That sounds good. All right. We're back in business. Okay. So this brings in the so what of finding an ocean on another world with volcanoes at the bottom. Now again, no sunlight, but this life exists without sunlight. How does that happen? Well, it turns out that there's 2 ways that life on Earth is based on. One is the one we know, photosynthetic life. That's everything that our food is based on. But this life found another way. It lives on chemosynthesis. It literally eats the heat and chemicals coming out of those volcanoes. And it's a fascinating ecosystem that's based on bacteria that do that, just like our ecology is based on plants that photosynthesize. These bacteria chemosynthesize, and they inhabit all these creatures and transfer that energy to them. So this is a truly seemingly alien world. This also sparked a debate that rages on till today. Where did life on Earth start? Since Darwin's days, he put forth his, warm little pools, tidal pools, all under the assumption that life on Earth was based on photosynthesis and therefore had to have started in the sun. But once we discovered this environment, we realized we had a bit of a mystery on our hands. Did life start out at the surface photosynthetic and at some point evolve to inhabit the deep ocean and be chemosynthetic, or the other way around? I don't have an answer for you. We do not have an answer to that question yet. But this then comes back to that Europa question. If life can start in this environment, then maybe it started in Europa's oceans. So the next we jump ahead is to the 90s. We're going to jump ahead like 20 years, but in 1995, the Galileo spacecraft arrived at Jupiter. And it was there, much like Cassini at Saturn, to kind of tour the whole system, look at the planet, look at as many of the moons as it could. But obviously of great interest was Europa. Now, one of the main things that we knew about Jupiter is it has an incredibly strong magnetic field. And in fact, Galileo carried a magnetometer on board. The other thing that we knew is that because the magnetic field is tilted and because the moon's orbits aren't perfect circles, that these moons not only travel through the magnetic field, but the strength of that field changes as they move around in their orbits. So they're under a varying magnetic field. Now, if anyone in here knows just a little bit of electromagnetism, You're probably seeing maybe where I'm going with this, but I'm assuming most people don't, so I'll give you a quick little lesson. If I take a conducting material, like a metal wire, and I stick it in magnetic field, nothing happens. But if I move it so that the strength of the magnetic field is changing, that will induce a current in the wire. Now, if I do this in just such a way that that current is constant, then that's the end of the story. Nothing else happens. But if I do that in such a way that the current is changing, that in turn induces its own magnetic field. So one of the things we started noticing is that some of these moons have magnetic fields not generated of themselves, but generated because of that interaction. But that does mean that something in the moon is conductive. Now we know that water is conductive, but it's honestly not great, but it does conduct. Now, later on, I will tell you, we found that Jupiter's magnetic field isn't only strong, it's also incredibly strange. So here's its north pole, which is far more spread out than we know Earth's to be, and then it gets weird. You look at the south pole, it kind of has 1.5 south poles, like there's the main one, and then there's one kind of off to the side. So this is producing a lot of varying magnetic field strength for these moons. So here we get to look at some squiggly lines. Honestly, astronomers spend more time looking at squiggly lines in code than they do at beautiful pictures. Sorry to burst your bubble, but we can get really excited about some squiggly lines. And this is a really exciting one, and I'm hoping I can get you excited about it. These are magnetic field readings. If you look over on the left side, you see a capital B. B is what we use for magnetic field strength and time. And these specifically are the squiggly lines produced when the spacecraft went whizzing by Europa. And the blip that you see is that induced magnetic field. The magnetic field of Jupiter causing a current inside some conducting material inside Europa, causing its own magnetic field. But when we looked at the strength of that magnetic field, it was way too strong for pure water to be explaining that. In fact, the conductivity that matched the blip was salty water in a range that could match our oceans. The plot thickens. So now we don't just have an ocean with volcanoes at the bottom, we have a salty ocean with volcanoes at the bottom. And if you know anything about biology, you know that all of life on Earth came from the oceans, and so to this day, even all the fluids in your body are not pure water, they are salty water. In fact, very similar still to the salinity of the oceans. This is why when you give someone IV fluids, it's always saline fluid. You give someone pure water intravenously, it can actually kill them. So we are not creatures that want pure water. You want to drink pure water, but you want in your body to be salt water. All right, so here's the setup. We know we have an icy crust. We know we have a subsurface salty ocean, and we're pretty sure we've got a volcanic sea floor. Now, to give you some sense of scale, what are the sizes we're talking about here? The icy crust is estimated to be between 5 and 10 miles thick. The ocean, I said, had more ocean water than all of Earth's oceans combined. How can that be in a little moon? That's because that ocean is anywhere from 50 to 100 miles deep. Again, Earth's deepest point in its ocean is 7 miles. Okay, so in addition to these blips and squiggly lines, Galileo also provided some updated, much better pictures than Voyager did. And so with Galileo, we were able to zoom in and see these cracks in even more details. You see a rare set of craters there. And looking closer, this was taken when Galileo was 219 miles above the surface. For comparison, the ISS orbits at 254 miles above Earth's surface. It got as close as 124 miles from the surface. I want you to keep that number in mind, please. 124 miles was as close as it got. The resolution of those images from the closest. So if you're a person working on Europa, your definition of high resolution images is 300 meters per pixel. Yeah, 1 pixel is the size of 9 football fields. That's your high res. And yet there's so much we can tell even with that data. Which brings us kind of to today. Now, we have not had another mission to Europa since Galileo in the 90s. We do have a spacecraft at Jupiter right now, Juno, that is taking some new images of Europa, which is cool. It's the first ones we've gotten in, 30 years. It's nice to finally be getting images again. But Juno was never designed to study the moons. In fact, its job is to study the interior of Jupiter. It has pretty much surpassed both its primary and extended missions. They've pretty much collected all the data that it can possibly collect, so they repurposed it to say, well, as long as you're still working, why don't you go take some pretty pictures of the moons? So it's not really what it was designed to do. So mostly we're working with Galileo data at this point, but just because the data is almost 30 years old doesn't mean it's bad data. It's just data, and you can do new fancy things with old data. So we've used modern computer algorithms to create 3D models of the surface in some areas so that we can then manipulate it and give it a little bit more of a depth perception to it. And we can see these whole cracks being cracked effect. We've also been able to reconstruct some of the recent tectonic activity. Now, we knew it was active, but we didn't realize just how active. Solar system is 4.5 billion years old, right? So we've got to keep that geologic time scale. There was a tectonic event on a global scale on Europa that took the entire surface and shifted it 70 degrees. And it happened just a few million years ago. The blink of an eye in geologic timescales. This is still a very active world. It is not calmed down at all. And it might glow in the dark. So this is not a real image, but we do have measurements that suggest that there are organic compounds on the surface. I want you to know the difference between saying there's life and organic compounds. Okay, organic compounds, think of that as the ingredients for life, and those things are all over the place, okay? Comets have them in spades. Saturn's moon Titan is covered in it, so that's not exactly rare. There's a reason we have life on Earth. That stuff is everywhere. But if it is on the surface, we also know that some organic compounds can fluoresce under certain illuminations and radiation, which there is lots of at Jupiter. And so, yeah, it could glow in the dark. And yes, the new mission would be able to see that. Another cool thing that we think might be on the surface are penitents. I have to learn that word. So penitents are things that on Earth form in very dry desert conditions that are high in elevation and are getting, you have ice that is in a very dry environment getting intense sunlight. And in that environment, the ice doesn't melt, it sublimates, goes straight to a gas. And when you do that in a certain way, what you're left behind are these spikes. Now on Earth, these things are a few feet high, but they are pretty weird and freaky looking. And on Europa, they think they might exist at heights of 50 feet high. And there are people that think they see in that 9 football field per pixel evidence that this indeed could be on the surface. The next mission's going to check for it. Another big question that again starts with I got curious, and so I asked, what about the temperature of this ocean? Obviously it's liquid, so it's above freezing, but how warm is it? It's got volcanoes at the bottom, but it's 50 to 100 miles deep. And what about the pressure? Well, yep, someone has looked into that. Someone has run models. Now you'd think, okay, you heat it at the bottom and then it freezes at the top. So it's warm at the bottom and cold at the top. Except water is weird. Water does something that most things don't do. As you get colder, it gets denser and denser and denser, and most things, as you cool them continually, keep on getting more dense, but water doesn't. It reaches a maximum density, and then it starts to expand again. Ice floats in water, because ice, even though it's a solid, is somehow less dense than liquid water. And this maximum density happens while it is still liquid, at 2 degrees Celsius. So 36 degrees Fahrenheit, just a few degrees, still above freezing, water reaches its maximum density, and from that point on, starts getting less dense. So what happens in Earth's oceans and in really deep lakes, the deeper Finger Lakes included, is they become stratified, where at the bottom there is a layer of water that is at 2 degrees Celsius that never changes. It's stuck down there because it is the densest stuff. And it sinks to the bottom, and there's no way to get it up. The currents are not strong enough to dredge it up from the bottom. It's just too deep. Now, that then is like, okay, so the coldest should be at the bottom, but there's volcanoes at the bottom. And so water does not, the convection is complicated. Thankfully, we have smart scientists who write really amazing code and can model this. The verdict is that everything would stabilize into a pretty constant temperature gradient after only a few million years. Again, pretty small time scale, which means that for the history of the solar system, this ocean has probably had a pretty steady temperature profile. And when they run the numbers, they estimate that the bottom of the ocean might sit at about 45 degrees Fahrenheit. Quite lovely for ocean water. Now, of course, hundreds of degrees right next to the volcanoes, but yeah, overall on a global scale, we'd expect those kind of temperatures at the bottom of this ocean. But what about pressure? Okay, on one hand, you've got much deeper water, so you'd imagine higher pressure, but also a lot less gravity. And pressure is basically gravity pulling all the above water down on you. So we run the math. All right, Earth's deepest point, we said, is the Mariana Trench. That's 7 miles, 12 kilometers deep. So a way to think about this pressure is to get to the pressure that's at the bottom of Europa's ocean. How far deep would you need to go in Earth's ocean? And the answer is there isn't a deep enough spot. If you wanted to get to that pressure on an Earth ocean, you'd need to go 13 to 26 kilometers deep, up to twice the depth of the deepest part of Earth's oceans. To put that in terms of atmospheric, you might have heard that Venus's atmosphere has a pressure that is 90 times Earth's atmospheric pressure. And that's equivalent to about 1 kilometer deep in Earth's oceans. But this is a pressure that's anywhere from 1,300 to 2,500 times Earth's atmospheric pressure. So now you might be thinking, okay, the ingredients for life are there, the temperature's good, the salt's good, but surely that pressure is just too crushing. Not if you're a water bear. I give you the tardigrade. The microscopic animals that won't die. I mean, short of ripping their bodies apart, there is virtually no way we have found to kill them absolutely dead. They can go into a stasis, they can completely dry out and exist in this desiccated form. They survive in space, they survive in nuclear disasters, and yes, we've tested it, they can survive at pressures that high. So there's Earth life that can survive that, even though nothing on Earth has ever demanded that you survive that. I have no idea how you get a creature so over-evolved as this one. So, yes, there is life that on Earth that could live in the environment we're looking at. So now we're really excited, right? the answer to where life started on Earth could lie in whether or not there's life in Europa's oceans. Because there's a difference between an environment that matches where life is on Earth now and an environment in which life can start. Those are two very different things. Life is everywhere we look on Earth because it has evolved and adapted to all these different environments. But it started in one very specific environment. And we have no idea what that is. We do not even have a solid hypothesis for how that happens. So the question is, we might have an environment in Europa that Earth life could survive in. But maybe that's not an environment life can start in. And if that's the case, we should expect to find no life in Europa's oceans. But if life can start in that environment, then maybe we would. And this comes back to the answer of where did life start on Earth? So if we found life in Europa, that might point us to the, maybe that's where life started on Earth. So what are we going to do about it? Well, obviously we're going to do what solar system explorers have been doing. We're going to send spacecraft. And we're going to keep on sending spacecraft because every time we go, we learn new stuff. We have answers that then just breed more questions. And also know that when you send spacecraft out, everything on it by the time it starts doing its science is like a decade outdated. So you're already thinking of like, okay, you're taking your science, but now I have something even better that I want to put on the next spacecraft, even though you just started doing your thing. So, just 2 weeks ago, we launched the next mission to Europa, JUICE. It's the Jupiter Icy Moon Explorer. I really think we're getting a little stretching it with some of these acronyms, but okay, JUICE. JUICE is a European spacecraft. Yes, you're like, why haven't I heard about JUICE? So yes, this is an ESA craft, successfully launched just 2 weeks ago, is on its way now to Jupiter. We'll get there in 2031. You need patience in this business. Things are very far away. But you've been lured here tonight to talk about another mission, and that's the NASA mission, Europa Clipper. This is NASA's next big flagship mission. That's the biggest class that you can send. And it is scheduled to launch October of next year. So we're like a year and a half out. It is currently in its final assembly stages, so they're finally putting all the components together and testing it, assembled slowly. This is all happening out at Jet Propulsion Laboratory. If you were to go out there, you could schedule a tour. You could go there. I have friends that go there, and you can go into the assembly bay. There's a viewing place, and you could watch this happening. So yeah, she's being put together right now, and we're really excited about it. Going to arrive, assuming this launch date holds, will arrive 1 year before JUICE in 2030. We're taking a bit of a faster route. That still feels like too long to wait, but okay. Now, the big questions. I mean, you think that, like, okay, we know the ocean's there, but again, let's just confirm it again, right? Let's really convince ourselves. You have to be a skeptic when you're a scientist. You're like, okay, convince me, let's just do that. But what specifically? Well, assuming that we confirm once again there is an ocean there, big questions, how deep is it? How thick is the ice sheet? What's the chemistry in the oceans? Can it support life? And how does material move between the ocean and the crust and the surface? And how in the world are we going to answer all that while we stay in space? Well, we're clever, that's how. So as I mentioned, Jupiter is a high radiation environment. And so the technique that Europa Clipper is going to use is the same one being used by Juno that's there now, which is to be in a highly elliptical orbit so that you are only close to Jupiter for a short amount of time while you whip around and then go back out where it's safe. This always reminds me of like how a cat attacks a snake. Like they sit there and then they just go in, pow, and then like back off. That's the technique you've got to use. Europa Clipper is going to do the same thing, except it's going to plan these orbits to clip past Europa with each pass. See the play on words? So we don't have a fancy acronym, but we have a play on words, because a clipper is also a type of ship, right? Yeah, see what we did there. All right, so how are we going to do this without touching Europa? Well, we've got some leads here. This is a terrain on Europa that's known as the chaos terrain. And what you notice here is that pieces that have cracks have not just cracked, but actually broken off and are now kind of off on their own. And this very much looks like what happens when you have sea ice break up on Earth. That's Earth on the left and Europa on the right. So we think the model that we're looking at here is that this is somewhere where there's a hot spot, similar to Hawaii or Yellowstone, where you've got kind of a plume of heat that's making that place in the ice thinner and cracking apart, which means the stuff, let me bring this back, the stuff that's between those, look at the stuff that's between those islands. There's no cracks. We believe that's because it's fresh. It has recently risen up through those cracks to fill in those gaps. And if that's true, that means that that could be some very recent, fresh ocean material that's just been brought right to the surface where we can see it from space. All right, but then there's radiation from Jupiter beaming down on this stuff. And what happens to it then? And does it ever get recycled back down to the ocean? And then there's the cracks themselves, all right? They have this very distinctive orangish color, especially if they are newer cracks. And if life had a color, it would be brownish orange. That's why Titan is orange. So many organic compounds just tend to have that color to them. So this is very tantalizing that these cracks appear to be life-colored. Now, it could be a lot of things, but still, could also be a way in which we have more recent water being brought up to the surface as these cracks spread apart, just like the mid-Atlantic ridge on Earth spreading apart and the mantles coming up and forming new ocean floor. Okay, so amidst of getting ready for Europa Clipper back in 2004, when Europa Clipper was an idea that it was a selected mission, we were getting ready, Cassini arrived at Saturn and discovered its moon Enceladus spraying stuff out into space through cracks in its surface. Now, I could give a whole talk about this moon, but I won't. Spoilers. This is another icy moon with cracks on its surface, and the stuff flying out of there is ocean spray from yet another subsurface salty ocean with environments at the bottom matching hydrothermal environments at the bottom of Earth's oceans. And it's shooting it into space for us. And Cassini flew through it, actually touched this ocean, and measured it, yep, about the same saltiness as Earth. All the ingredients for life are there, evidence that there's hot rock and hot water interacting at the base. We know more about this ocean now than we know about Europa's. So this kind of made Europa people go, oh, that's really convenient. It'd be nice if Europa did that. And they started dreaming of, what if Europa did that? What if Europa had eruptions on it and had plumes? Well, again, old data isn't bad data, so some people dug into some old data, some Voyager and Galileo data, and convinced themselves that maybe that's a plume. And I'm going to take you back to the squiggly lines because the blips actually had blips on top of them that were not well understood at that time. And when they looked back at it, they said, you know what could explain the blips on top of the blips is if the spacecraft also flew through a plume. Now, I do not want you, I promised my friend Julie, I will not let you leave this room thinking that we definitely know there's plumes on Europa. She is one who is not convinced yet. Scientists are skeptics, so this is not something we have confirmed. What we have confirmed and we feel pretty confident about is the Hubble Space Telescope was able to measure that on one side of Europa there is a thin I don't know that I'd call it an atmosphere, but we'll call it an atmosphere of water vapor over the surface. Whether or not that's coming from a plume or from just sublimation from the icy surface is not yet answered. But somehow water vapor is making it above the surface. So this is kind of what we hope is going on there. I love how Aya's making a little photo bomb up here, like, I erupt too. Yes, but we're not talking about you today. I love that whoever made this put these things in the ocean and one shooting up out of the volcano. I don't know, they look like little happy faces. Maybe they're supposed to be jellyfish, but it's generally supposed to be the idea of like there's happy life down there, and maybe the life's being shot out of these plumes. We would call those cryovolcanoes. So it's a volcano where the mountain's made out of water ice and the lava is water. So fun fact, you're all 60% water, so as far as Europa is concerned, you're a lava monster. So great, this is what we think's going on. What's Europa Clipper going to do about it? So I'm going to do a quick run through of the payload. That means all the scientific instruments on it. Now, I am not an engineer, which means I'm not going to talk about the instrument itself. I'm going to talk about what it's going to do and what we hope it's going to tell us. I'm also going to move through this kind of fast because I don't want us to get bored looking at picture after picture of metal thing that is not terribly interesting. But let's start with the thing that all spacecraft should have, a camera. All right, this is a camera. I know it's not obvious, but it is. So this is actually one of many cameras on board. This is a visible light camera. It can also see a little bit into the infrared, but basically the same as your eyes. Now this is going to be a very high resolution camera. We are going to map 90% of the surface in at least as good a resolution as that Galileo high resolution, the 300 meter per pixel. But the high resolution that will be the new definition for Europa will be 1 meter per pixel. Now Mars still has its beat with the high-res camera. They have 1 foot per pixel, but 1 meter versus 300 meters is going to be a massive upgrade. Okay, the European people are literally drooling at the thought of resolution at this level. And we're going to do that because not only is the camera really good, but instead of getting to within 124 miles of the surface, that clip past Europa will pass as close as 15 miles above the surface, which you can pull off because, unlike Earth, it doesn't have a thick atmosphere, so you can get a lot closer. All right, what else are we doing? Spectrometers, right? Spectrometers are your robotic noses, basically, except they smell with light and color and tell you what it's made of. That's what you need to know about a spectrometer. This is an infrared spectrometer, and it's going to measure infrared light. That's mostly what we think of as heat. It's past red in our vision. And it's reflecting off of Europa's surface, both from the sun and from Jupiter. Jupiter also is very hot, puts out a lot of infrared. And it's going to be looking for organics by looking at the colors that are being bounced off the surface from that. So things like sulfates and carbonates, things that we know life likes to have. All right, how are we going to answer that question of thickness of ice? Ice penetrating radar. And this is a technology that we have been using on Earth for quite some time. Up there is someone who's in an airplane flying over an ice shelf in Antarctica using his radar to measure the thickness of the ice. And here's someone sitting on an ice shelf in Antarctica with their radar instrument around them. So this is something we know how to do very well, so we're very confident that this will work. All right, this is going to help us determine the structure and thickness of that icy crust. Very important. Magnetic fields, right? Obviously, we want to take more measurements. Magnetic fields have taught us so much. They're the thing that discovered the ocean in the first place. So 25-foot-long magnetic magnetometer boom will be attached to it. We're going to give more details on this. This might help us pin down the salinity with more accuracy. Also, the depth of the ocean, right? We could get more specific measurements on how much ocean we expect. It can also even support an idea of how thick the ice is. Ice is a very poor conductor, but it does conduct. All right, there's a problem though with measuring the magnetic fields, and that's that Io's hot surface shoots plasma off of it. Plasma is what the sun's made of. That's when you heat gas beyond its capabilities and you rip all the electrons off of the atomic nuclei and they all bounce around freely. And when that then is pushed by Jupiter's magnetic field onto Europa, it can disrupt its magnetic field. So how do you disentangle the magnetic field readings that you want from the ocean versus those that this plasma is causing? Well, you slap on a plasma detector so that you can be watching what the plasma is doing, and therefore you can take out the effects of that plasma. And also, guess what? The plasma detector can help you with determining the thickness of the ice and the depth of the ocean. I think we're kind of getting the feel for everything, like, oh, and guess what? This will help measure the thickness of the ice and the depth of the ocean. Because you don't want to make that measurement with just one instrument, right? You want to confirm it by making multiple measurements in different ways, and hopefully all of them pointing to the same explanation. This is Occam's razor, right? We want to eliminate all other possible explanations for this and know that we've arrived at the right one. All right, radio, not just helpful for talking back to Earth, but also can help with measuring the tidal shifts, the subtle changes in gravity. Let's remember that this is, remember I said lubrication, right? This is a decoupled object. Decoupled, to be broken apart. You've got a solid rocky core and you've got a solid icy shell, but those two things are not connected to each other. One can slosh around on top of the other one. And so by using radio waves, you can start to sense little changes in gravity that give you a clue as to how that's happening. Also supports finding the thickness of the ice and the depth of the ocean. Then there's a thermal camera on there, so that's now pushing well into the infrared. And this is very much not Europa. This is actually Earth. In fact, this is taken by the actual camera that's being put onto the spacecraft, taken out the window at where it was developed at Arizona State University, looking out onto Tempe right before, during, and after sunset, to illustrate the concept of thermal inertia. Now, inertia we usually think of as like, how hard do I have to push on something physically to get it moving? Same thing, only it's with heat. The pushing is done with heat, and the movement is how much the temperature changes. So if we look at the top image where the sun is shining, we see the windows on the buildings are very bright. Okay, red means it's reflecting a lot of infrared light. Also, the rocks on the mountain, most of them have gotten pretty hot, with the exception of one little band there. As sunset sets in, and eventually after sunset, we notice the windows go cold immediately because they were just reflecting light. So they don't have a lot of inertia. However, a lot of those rocks stay warm for a while. So inertia is all about finding out how easily does it heat up and how easily does it let go of that heat. And that can tell you a lot about the texture. So things like bare rock versus gravel versus sand all have different thermal inertias. And so we can actually pick up a fine scale surface texture using this. And that's very hard to see with your visible cameras, even at that 1 meter per pixel scale. Again, spectrometers, we want to sniff things out. This is a UV spectrometer. So this is, we could use it on that atmosphere that we detected, but this is one of those, like, we're hoping there's plumes, because if there are, we can use this to figure out what is in those plumes. Also can point it at the surface and get an idea of what chemicals could be on the surface, but this is one where we're like really hoping like there's plumes and we can use it on a plume. All right, then we got a mass spectrometer. Instead of using color to sniff, this one uses mass. It literally takes in substances, not light, but substances, and then separates them according to individual atoms, because each element has a unique weight, has a unique mass. And this is going to be able to be used on the atmosphere by actually scooping stuff up, because we can fly close enough to do that. And again, crossing fingers, could use if we fly through a plume. We're really kind of hoping for an Enceladus type situation here. All right, and then we have finally a dust analyzer, because, you know, we'd love to pick up something other than gas. If indeed there's eruptions coming off the surface, we would hope that some solid matter, very small, and we call very, very small solid matter dust, makes it up into the atmosphere again, and that we can actually scoop some up and tell something about that surface composition. Again, even if there aren't plumes, we know there's a water vapor layer that we can sample from. All right, so that's going to be super awesome in 7 years. So I'll have to come back, Drew, in 7 years to report. You totally need to have a launch watch party for this one next year. Yeah. Oh, yeah.
Where's it launching from?
It's launching from Cape Canaveral. Yeah, one this large is going to launch from there. Okay, so what do we do once we have all this amazing data and this new definition of high res and all this information? Will we be done? No. What do you think we might want to do next? Well, we want to do that, yes, and we are planning a separate mission to fly to Enceladus, maybe even collect some of that ocean spray and bring it back to Earth. But what do you think we'd want to do next with Europa? Boom! Land on it! So Europa Clipper is seen as a recon mission as well for a future Europa lander. I love the little logo they've come up with, because if you've seen the movie Europa Report, you're probably thinking it looks like tentacle coming out and attacking the lander. It's actually supposed to be like a stream of water coming out, and the dots in it are like organic things. But I'm sorry, that's sea monster tentacles reaching out there. They need to redesign that a bit. So you can see here what it might do. It could do things that like a Mars lander has done. Scrape the surface, put it inside an analyzer, look at that. Okay, right now we can't do this because 9 football field per pixel. No, we cannot pick a safe landing spot with that. If anyone watched the OSIRIS-REx mission at Bennu and what it went through, the problem was that we used thermal inertia and said, no, we think it's got a sandy surface. But we had not seen the surface, and we designed this delicate instrument to go down and gather up some sand, and we got there and the thing was a boulder heap. We had to throw out anything that we thought of as safe and redefine it completely. We don't want to run that risk again, so we are going to wait till we get the Europa Clipper data to start thinking about this. There's another problem with this, and that's the high radiation environment of Jupiter. We said that Europa Clipper is zipping out. If you land, that's it. You can't get away. You're stuck there. Now, one answer to this is to use Europa, like our moon, is tidally locked. So it rotates at the same rate it orbits, so one side is always facing Jupiter, which means if you land on the far side, you can use the moon itself to block a lot of the radiation. There is a downside to this, though. You won't get a picture from the surface with Jupiter in your sky. I know it's a trade-off, but darn it. All right, so once we've scraped the surface, what would we want to do next? Get through the ice, right? Okay, now it's 5 to 10 miles of ice. We'll get to how we're going to deal with that in a minute. But assuming we can get through that, one idea is, I don't know, I'm a Stranger Things fan, go to the upside down, have a rover that drives around on the underneath of the ice using buoyancy. This is an actual prototype. It's about 1 meter wide. You can see someone standing up on top of the ice there. It was designed at JPL to rove on the underside of an ice shelf. However, this probably won't be what we want, because what we have learned about Earth is that this is not where you find a lot of life. This is where it's very cold, And yeah, with oceans as deep as Europa, probably not where you're going to find most of the life, which means we need to go full-on submarine. This is an actual photo. This is ice fin. An ice fin is a prototype. It's about 13 feet long that has been developed and is being used. It's been used for several years, gone down to Antarctica and gone beneath the ice shelves there. We're very excited that the lead of this mission, Dr. Brittany Schmidt, is recently joined Cornell. She was also just named one of Time's 100 most influential people, so she's been in the news quite a lot. She just had the whole red carpet experience. It's all very exciting. She goes down to Antarctica or up to the Arctic every season. She likes the cold, if you haven't figured that out. She loves it. So here she is loving the cold so much. She likes this, all right? I'm not going to yuck someone's yum. But here's what they do. They drill through the ice and they lower ice fin down through the hole, and then it swims around. So like a Mars rover, the goal is for it to be able to navigate itself, right? But in the meantime, the cool thing is that while we are testing out this eventual, way decades in the future, submersible to explore Europa's oceans, in the meantime, we are using it on Earth's oceans, and it's actually providing very valuable information in monitoring climate change and the health of the oceans. So, yeah, you get that too. Now, if you go to the IceFin website, there are some really cool videos you can watch there of this thing floating around and of what it's seeing down there. It's really cool. But let's deal with the elephant in the room. How do we get through 5 to 10 miles of ice? Well, heat, drill, just push right through. This is probably my least favorite illustration. I mean, aside from the fact of how it makes you think the ice is that thin, it seems to be just like drill plowing through. The other thing I have a problem with is the hole. All right, anyone who's ever done any ice fishing knows that it's hard to maintain a hole that you can go down, and Brittany will tell you that they have to fight constantly. The hole keeps trying to refreeze. Also, this is not drilling through ice on top of a lake. You're drilling through the surface of the world. Okay, what happens if you drill through the Earth's crust down to the mantle? Right? The deepest we've drilled on Earth, I think, was it 12 kilometers? The borehole in Russia, and they had to stop because the heat was so bad it was melting all the drills. So I don't think we want to create our own cryovolcano. That's not going to serve our purposes. So we can't just bore through. This one I'm really like, you think you're going to fire thrusters and just push through? Or crash into it. I'm not really sure what's going on in this picture, but it does show one thing that we think is very promising, which is heat. All right? Ice does melt. But what if we give up on the idea of maintaining the hole? There's a very elegant and simple solution. Just make it hot. This is a prototype where you'd have instruments in there and it's encased in something that just gets hot. Patience. If we can wait 7 years for it to get to Jupiter, we can sit there and wait for this thing to slowly melt through the ice and keep sinking and sinking. Let it refreeze behind it. Sure. And just keeps on going down, down, down until it eventually pops out the bottom. Now then you have the question of, okay, how does it get a signal? Back out. We are still a long way off from figuring this out. I'm not going to tell you we're ready to do this tomorrow, but the point is we're thinking about it. And Europa Clipper is kind of that next step in figuring out how to do this. And so that is basically where we're at right now. And I'd like to know if you have questions. Yes.
Actually,
all right.
Hold on a second. What I'm going to do is I'm going to take the microphone over here so that the people
yes,
on the
that's
live stream
really
can
good.
hear it as well.
Okay, 2 questions. One, would the UV meter also measure if it fluoresced, if there was fluorescence?
So it could pick up that fluorescence. The kind of fluorescence that we think it might have would be more in the infrared. So something that our eyes wouldn't see. So unfortunately, like if astronauts went, you might not see Europa glowing in the dark. But yes, several things fluoresce in different wavelengths, and if there is something fluorescing in the UV, it should be able to pick it up.
Or in the infrared?
Or yeah, the infrared instrument is the one that we're designing to pick up that fluorescence if it is there.
Okay, the second question is, in the vein of how people didn't think there was life at the base of the ocean, couldn't it be possible that these missions saw life on the surface of the planet also?
So whenever a question about what life could be and where it could be comes up, I have to default back to we have a data point of 1. There's not a lot I can scientifically conclude from that. Which means that we have to admit that life could be anywhere, anyhow, we don't know. But we have to start somewhere. And so we are starting from life as we know it. It's a place to start. We have spent the last 20 or 30 years of space exploration answering the question of where. Where do we think we should be at least starting this search? Let's keep in mind, why haven't we found the aliens yet? Because we really haven't even started to look. We're just starting that. We're at the cusp of the age of actually looking for alien life. So we're going to start with what we know. We're going to start by looking into environments that we have identified throughout the solar system, either current or past, that are similar to environments on Earth where we know life can exist. So this has been the search for habitable environments. The next step is to see if they are inhabited. But could there be life at the surface? As far as we know, no. The radiation is way too high, and you're exposed to space, and a tardigrade could survive there, but it would be in stasis, I'm sure. It wouldn't be like happy and having a little party with its tardigrade buddies.
We don't know exists that could thrive in an environment like that.
I cannot say that there couldn't be. We are going to start with what we know and go from there. But yeah, you're right.
You're saying
we can't
that
rule it out.
definitively. We do have at least one question from the online web, the chat. It says, since ice crust is so dynamic, won't there be active places where the ice is thinner?
Ooh, that is an excellent question, and yes, we totally would expect that the thickness of that ice is not constant. Chaos terrain would certainly be somewhere we would expect the ice to be thinner than the global average. I think a couple years ago, 2019, Cornell hosted the Europa Clipper PSG, the Project Science Group meeting. So every year, the scientists on a mission get together while it's being planned to just, let's all see what we're doing, catch up. And we held it at Cornell, and I got to organize it. It was fun. And one of the things that every Europa PSG host does is create their version of the monolith from 2001, A Space Odyssey, because Europa. And so we decided to do it up big. We built ours aluminum almost to scale, and then we covered it with Vantablack, the blackest substance there is. It's not even a paint. It's a surface of nanostructure tubes that light goes in, bounces around, and never bounces back out. To walk past it is a little disconcerting because it's like 9 feet tall and just looks like a void. So where was I going with this even? This is something like this cool monolith thing. The question was about that. So, okay, yes, that's where I was going. So we also, as a tradition, took a coffee can, and we had a card for each scientist to fill out, and they were supposed to write, like, what do you think we might discover? And it was anonymous, right? You could be as wild as you wanted to be. You could drop it in there, and nobody was going to look at it until Europa Clipper had concluded its mission, and then we were going to crack open the coffee pot and coffee can and see who was right. And I will reveal what I put in. I put in that we will find that there's places where the ice is less than 1 kilometer thick. So you know now, so in like 7 years from now, you hear that announcement, you'll know that I was right.
And you called it. We've got it on tape here.
Yes,
So.
it's on record.
And any other questions here locally? All right, we got a couple.
Thank you. Do the magnetic poles of Europa ever switch, and like how, since there's kind of more than two of them?
So I'm going to go back. They are dynamic. There was a great animation that I kind of had up and didn't really talk in detail about, so I'll find it and put it back up there. There it is. So because, again, everything's changing, and so it's a bit of a feedback loop. It's traveling through a changing magnetic field. The current is changing, and therefore the magnetic field is changing. Now, what are the colors here? I got to make sure I read it correctly. Green is the one that's due from Jupiter's field, from it being tilted from its equator. And the blue is due to Europa's orbit being tilted. So all of these tilts are what creates the changing, like it's not just staying in the same band. So you can actually break the magnetic field up into those two components, and as you can see, they are oriented differently because of the geometry of that. So the answer is it changes, and yeah, not very straightforward. It's certainly not a simple north-south pole like you see at the Earth.
All right, good question.
Going back all the way to those life underwater that eat the heat,
Mm-hmm.
does it interact with its environment or regulate its ecosystem similar to how we interact with trees with the carbon dioxide, oxygen in and out?
Yes, I will say I'm not a biologist, but I love how you
Me
said
neither.
eat the heat. I'm going to steal that. It's a great thing. Yes, it is kind of its own self-contained ecosystem. It does not, you could wipe out all photosynthetic life and this stuff would not care. So it is its own ecosystem down there. It does interact, right? Things die and float down to the bottom. Fish swim up and down. So it's not that there's zero interaction, but it is not dependent on anything to do with the surface life. So yeah, everything is in the same way that we think of plants as the basis, this bacteria is its basis. And so the bacteria eats the heat and the chemistry, poops something out, and then everything else can eat the poop. I mean, I hate to put it in simple terms like that, but let's face it, cows pre-digest grass for us. You know, that's how we consume a vast variety of things in our diet. There's lots of plants we can't digest.
Yeah, so I had two questions. My first one was out of curiosity. I know you said that the South Pole for the magnetic field of Jupiter, there's like just one random spot. Does that have any relation with the red spot on Jupiter or not?
Ooh, it's tempting to like go there, but I don't think it does.
So it's just a random one there.
I think it's just I'd have to look it up. I feel like if it were tied to that, a bigger deal would have been made out of it, honestly. So I'm not going to say definitely not, but I don't think it's tied to it. Also, what we saw is like it changes. It's not stable like this, whereas the red spot is apparently very stable. And no, we still don't have a good answer for what is sustaining it and what is keeping it so stable.
Okay, and then for my second question, as far as you're aware, is there like a plan for the Jupiter Clip, the Europa Clipper, I'm sorry, to try and aim for the chaos spot?
So again, we're going to map 90% of the surface is current plans there. You know, each time it passes by, we will get to measure a swath over the surface, and then we stitch them all together. So it's very much like, imagine paper mache, where you just kind of like lay one strip over, then you lay another strip over, and we just keep on doing that until we've imaged 90% of the surface at least once. That will definitely catch several of these chaos terrains. And so we will definitely also try to see if we can hit those chaos terrains with that highest resolution, because they are a high priority target. So yeah, we are going to probably get some really nice images of that terrain.
And got a question over here.
So you mentioned that there are several moons in the solar system, like Enceladus, for example, that have similar characteristics to Europa, like the icy ocean, the geological activity. So I was wondering why Europa is considered like such an attractive target compared to the other potential targets?
That's an excellent question, because I said that initially they saw, oh, it's just another icy satellite. It actually turns out that we have evidence that Jupiter's other icy moons, Ganymede and Callisto, also have liquid water layers underneath their icy surfaces. So does Titan, in addition to having the methane seas and lakes on its surface, do a whole talk on that, has a liquid water ocean underneath its surface. So what is it that separates out Europa and Enceladus away from these other worlds possibly having liquid water? And the answer is what's at the bottom of the ocean. Because what we think is going on with Ganymede and Callisto, and probably Titan as well, is that their oceans are sandwiched between ice layers. Where's the fertilizer? Ice on top of water on top of ice. There's not a lot there to support life. But you get a rocky bottom to an ocean, right? What do plants need to grow? They need soil. Rocks have components in it, silicate-based rocks, I should say, because we've decided that chunks of Titan's surface made of water ice are also rocks. So silicate-based rocks contain lots of compounds that we know that life likes to use. Just look at your vitamin bottle, right? So we know that a rocky bottom provides a lot of those nutrients that you're going to need. So the special thing about Europa and Enceladus is that with Europa, we're pretty sure, and Enceladus, we know that the bottoms of the ocean are warm rock. And that supports ecosystems here on Earth.
Another question?
Follow up.
Just a quick follow-up. So since we know with so much more certainty on Enceladus that the bottom is rocky and warm, why is that not the target, and why is Europa considered like higher priority?
As I kind of alluded to but didn't dive too much into, Europa Clipper had already been selected and was already deep into development when we arrived and saw the plumes coming out of Enceladus. And there was murmurings that, gee, if we'd known about that, maybe we wouldn't have targeted Europa. Because even though Europa is a bigger moon, okay, Enceladus is smaller, like a lot smaller. So Europa is like the size of our moon almost, and Enceladus is the size of like the British island. It's small, and that's why it was such a shock to us that it had an ocean. We did not think it was big enough to sustain an ocean. So Europa could potentially support more life, potentially more complex life even. And estimates for Enceladus, like they did the estimates like how much biomass could Enceladus support, and they added it all up and it was the same as like one whale. For the whole moon. So Europa's still a target of like, there could be much more interesting life there and more of it.
It's a lot closer.
And it's closer. I don't know. The outer solar system's all pretty far away, but it is closer. So yes, relatively it is closer. Yeah, Saturn's twice as far away as Jupiter. Okay, not going to deny that. So the answer pretty much is that we were already planning on going to Europa. Obviously, the moment we saw what Enceladus was doing, Cassini was never designed to do what we did with it and fly through the plumes. We immediately started planning like, okay, we obviously need an Enceladus mission. And in fact, the decadal survey that just recently went down, that's every year, every 10 years, the planetary scientists get together and kind of send a wish list to NASA. And this was the one that NASA agreed we needed a flagship mission to Enceladus, but they bumped it to the next decade in favor of a flagship mission to Uranus because we know nothing of the ice giants out there, and timing matters. We know that weather on Uranus is interesting during equinox, not solstice when Voyager 2 was there and it was boring. If we start now, we will time it to where we'll arrive during equinox. If we wait another 10 years, we're going to miss that. And so Enceladus is going to keep spraying its ocean into space. So it can wait, even though we really would love to go there. There's only so much money to go around. So next decade, we will be doing the Enceladus Orbi-Lander.
And on top of that, the technology, the sensing technology will have had a whole decade.
We're going to learn all this stuff at Europa, might inform what we do in Enceladus. But yeah, Orbi-Lander, it's going to we're going to go straight for orbit and landing on our first shot.
Just a little bit of a tangent off of this, but for those of you who might remember the moon landings, some of us were actually around for that. Just recently, they actually when the astronauts returned those lunar samples, they actually reserved a portion of them in a sealed unit, and they said, okay, we're not going to touch these for 50 years because we think in 50 years the technology to examine these samples will have improved so much greatly that, and so they're just now, looking at those new samples. So there is some benefit, if you will, to
waiting.
And
that's also, you're making a great argument for sample return. The idea that if you bring samples back, you can do so much more than what you can send on a spacecraft, and it's the gift that keeps giving. You can curate it and dole it out slowly and make it last decades I said, like, once you get there, everything on your spacecraft is a decade or two outdated. Sample return, you don't have that problem. But as hard as it is to get there, it's even harder to come back. So, But yeah, people would love to do an Enceladus, like fly through the plumes with some aerogel, and then like bring it back. But I mean, sample return to Saturn, we're still trying to do sample return from Mars.
Right.
So I think sample return from Saturn's very ambitious.
Although the Saturn sample return from Mars actually is going to happen. The Curiosity rover has made how
Perseverance.
many? I'm sorry, Perseverance. Thank you.
Well, we've got 24 or so, and it just dropped the depot, and then it made pairs.
Right.
And so it just dropped one set of pairs on the surface, and the other set stays on the rover. The default plan is for the fetch helicopters to go get the ones that are on the rover. But just in case, like, the rover goes off a cliff or something, we've also dropped them on a surface in a place that we know where it is, and we can go get those as a backup. But getting those samples back on Earth is pretty much the only way we think we'll get enough data to convince ourselves whether or not we see evidence of past life on Mars.
And one of the comments we got from the from the chat was acknowledging your proper pronunciation of Uranus. Maybe you could take a moment to touch on that. I realize that's.
You're going to let me get on my soapbox here.
Please. I used it a couple of weeks ago when we had sixth graders in here.
Right. So I did another talk here a while back, What's in a Name, and I always love to bring this up. So when I first took this job and I realized I was going to have to talk to kids about planets, and I really said, okay, well, there's a very important question. How am I going to say that planet's name? And I decided, regardless of what may happen, I want to say it correctly. So I set out to find out which one was correct, Uranus or Uranus. And as I dug, I found out that kind of neither, because this is one of those kind of places where Greek and Roman mythology bled into each other a little bit, and that the Roman god of the sky was actually a Latinized, they took the name straight from the Greek. And the Greek god of the sky was Uranos. So in Greek, that first syllable would be pronounced as an U, not a U. Now, you Latinize it, and yes, then you pronounce it as a U, but considering all of the issues we have, I decided to come up with a compromise and say Uranus, especially since we're going to send a flagship mission there. I'd really like it if the headline stopped making all the jokes.
There you go.
But yes, so spread the word. We're all going to say it Uranus now, because that's awesome.
And I have to give props to the educators here at Kopernik that have to deal with that every time a 6th grade group comes in here.
See, I love it because then I get to follow up with that.
There you go. Exactly. I actually have a question. Is you said that the Europa Clipper is being constructed. Now, is it just the instruments are being constructed, or the whole space frame?
The instruments are done, as far as I know. So what's happening now is they're, for the first time, putting the instruments together on the actual spacecraft bus. Mm-hmm. And that's what it's called. It's called a bus. And so that then causes the issue of, like, we've never tested it all together as one thing. And this has actually caused problems with spacecraft in the past, where everything was tested individually, but it wasn't tested as a whole. To some extent, we cannot test it perfectly, and there's always things we don't anticipate. But that's the stage it's at now, where for the first time we've got all the separate components They're all pretty much finished and brought together, and now we're starting to kind of piece things together and test along the way. And then sometimes you take it apart again and you look at it, what happened during the test, and then you put it back together. Spirit and Opportunity got like assembled and disassembled a few times before their final assembly. So that's kind of the stage we're at right now.
And I don't suppose you'd consider putting it, so, you know, how like you can go on YouTube and you can see nest cams of an eagle or something like that, and actually have sort of a YouTube channel that you could watch it being.
They did that for Perseverance, and I have not heard of them doing it for Europa Clipper, but there might just be a constant JPL assembly bay cam. I'd look into it.
Yeah.
They could just have one that's always running there. They're always doing something cool in there.
We have a couple more questions here.
You're talking about like sample collection earlier and stuff. I know that NASA like purposely crashed one of the satellites into Jupiter or into Io, I forget which one, to like protect Europa's oceans from like contamination of Earth. Do you know like if they've addressed the issue for the landing mission or for collecting data, how they plan on doing that without a Earth microbes or bacteria getting?
You ask a very important question, and there's a whole planetary protection division of NASA that asks those exact questions. So yes, we often dispose of spacecraft in a way. Cassini was crashed into Saturn for that reason. Yes, as we saw with the tardigrades, we do try to sterilize anything we're going to send to space, but you know, you can't be sure that you've killed everything. So there's the concern of, yes, contamination. In fact, there's kind of a no-go zone around anywhere that we've landed or driven on Mars, which is the idea if we go back, don't go there to do your science because it's possibly contaminated. There's also planetary protection the other direction. We're getting to talk now about like how can we bring these Mars samples back safely, knowing that we're not going to contaminate Earth with something from Mars. And there's kind of the uncomfortable question of how do you make sure you can kill life that's alien, that you know nothing about? Because we cannot rule out the possibility that there is still microbial life in the rocks of Mars, or that it's in a stasis that we might awaken. We don't think so, but it's also something that's like, we really should cover all bases, right? We don't want to turn it into a sci-fi horror movie.
All right, we got one more here.
Yep.
So considering the depth of Europa's oceans and the pressure that's experienced there, and also the possibility or the likelihood that most of the life on there will be found at the bottom, do you know of any efforts engineers are making towards generating some technology that will have the ability to dive down that deep with that amount of pressure? Like, are they able to mimic those conditions on Earth? Because you can't really run that here.
Right, so that is one of the questions that, yeah, we don't yet know how to build something that could withstand that pressure, but you know, we managed to go from not knowing how we'd make it to the bottom of the Mariana Trench to making it to the bottom. We managed to eventually land on Venus. We know the basics of how you design something to withstand pressures. It will be a matter of, yes, building it up. I do not know if we currently have a facility that can simulate that amount of pressure, but it's definitely something we'll have to contend with. And yeah, how to properly test for that, that's for the engineers. Oh, see, there's a question back here.
A couple more. All right.
So with the amount of radiation that's coming off of Jupiter, does that make any difference for the possibility of life in the oceans? Would it be more radiated, or does the magnetic field or the ice crust around Europa kind of protect it from that?
The crust would protect it, but it's also a possibility that the radiation might be helping the life. I mentioned one of the instruments was going to look for the fact that radiation might actually be creating some organic compounds on the surface, and if there is a process that brings stuff up to the surface, there may also be a process that sends stuff from the surface back down. And so the radiation at the surface, even though that might not allow life to happen there, might actually be helping life down in the ocean. And that's why I said one of the big questions is, what was the material exchange between from the surface down to the bottom of the ocean and everywhere in between. But yeah, radiation can actually be a helpful thing for life as far as what it can create.
Going back to like the Planetary Protection Division, so like how did the satellites or spacecraft not contaminate like Jupiter, whatever moon we decided to crash into, and like what goes into making that decision, I guess, because like aren't they technically contaminated because they have like to them an alien spacecraft on their surface?
So we've never crashed anything into any of these outer solar system moons. We've always disposed of them in the atmospheres of the planets. Now, can I say for sure there's no life in the clouds of Jupiter and Saturn? No, I can't. But we know with the way we crashed it that we basically vaporized it. And as I said, you can kill a tardigrade if you rip its body apart, all right? So if we reduce it to molecules and atoms, we're pretty sure we've killed everything. And so we do think of a way that would truly sterilize it in a way that we can't do here on Earth because that involves destroying the spacecraft. But yeah, the landing of things on Mars, yeah, we don't dispose of those. They just stay there. And the hope is that the Martian surface conditions are so inhospitable to Earth life that even if something survived, again, it'd be sitting there in stasis. There was a very controversial thing that happened a few years ago with an Israeli spacecraft that crashed on the moon and found out after it crashed that it had tardigrades on board. And a lot of people were like, oh, that's cool, tardigrades on the moon. And we were like, no, that's a horrible thing. How did that happen? And it was a whole thing where the government actually didn't know they were on there, that a private company that was subcontracted snuck them on there. So no, we weren't happy about that at all. We did not like the fact. Now, are the tardigrades dead? Maybe. If they're not, are they ever going to pop to life and colonize the moon? Probably not. But yeah, it is something to think about. The Martian surface, we're pretty sure, would render any life, if not dead, inactive. But still, it's not the place that you'd want to go to take samples to find out if there's life on Mars, because you might just find that Earth life.
All right. Well, this 90 minutes have just flown by. First of all, thank you very much, Zoe, again, for just a stunning presentation.
Thank you very much. Great questions, y'all.
If there are further questions, I think Zoe will probably hang here for a little while, although she does have to drive back to Ithaca. So next week, our talk is going to be called "How Tiny Fossils Can Answer Large Questions About Our Earth Systems." It's a BU geology professor talking about the work that she does in ocean exploration. The weekend after that is Southern Tier Robotics Competition. This is a group of high school students that build competition robots that are literally probably about 2/3 of the size of this table, that then go and compete. So they'll bring their robot up here, talk about how they built it. And then the weekend after that, the Friday after that, is Destination Neptune. So we're going back into space on May 19th. For those that are interested, that maybe here for the first time, we will. Let me see. We'll start in about 5 minutes. If we can meet out in the lobby, we can take you out, and so you can at least see some of our telescopes. See our largest telescope, our 20-inch reflecting telescope. So thank you very much for coming tonight. Hope you enjoyed it, and look forward to having you come back.